right? So let's express sine of z in its real and imaginary parts. So sine of z. So how are we going to do this? Well, um, sine of z we can define in terms of exponentials. So just the sorry. So the Euler's formula can be generalized to not just e to the I theta, but e to the I z. So e to the I z is equal to cos z plus I sine z, right? And yeah, mm, yeah. And so sine z um, can be expressed as e to the I z minus e to the minus I z over 2I. Okay. Okay. So, sorry, let me just think a little bit. Mm, yeah, that's fine. Okay. Now let's turn the z's into x plus I y. E to the minus I x plus I y over 2I. So that'll be e to the, let's see, minus y plus ix minus e to the y minus ix all over 2I. And now we can separate, you can say it's e to the minus y times e to the ix, y to the minus ix over 2I. And then the e to the ix and e to the minus ix. Now x is real, so we can use kind of that same formula again, or that original Euler's formula. Cos x plus I sine x minus e to the y. And this e to the minus ix will be cos x minus sx. Okay, so now things are looking up. Um, we can collect the real parts, so that will be, let's see. Wow. Um, yeah, let me put the 1 over 2I here at the front. So we'll have cos x, or rather 1 over I, I'll put at the front, to the minus y minus e to the y over 2. And then I'll have plus I sine x e to the y plus e to the minus y over 2 there. And then note that 1 over I is actually equal to minus I, right? How do I know this? By multiplying by I top and bottom, we can realize the denominator. So here I multiply by I top and bottom, and I squared is just minus 1, so it's minus I. 1 over I is minus I. So we get yeah, we get sine x. Well, like the I and the I here cancel, so we get so for actually this will give us the real part. So sine x, and then that can be written as cos y, right? This thing, and then we'll have well, let's see. So 1 over I will become minus I, so this will become basically the imaginary part. Well, the minus I, I'll take a minus sign through to here to flip the sign of the subtraction, and then that will give us sine y. So it'll be plus I cos x sine y. So that's cool. Okay, so yeah, these are the real and imaginary parts of sine z. So if we want that to be 0, of course we want both um, the real and imaginary parts to be 0. Uh, and now remember that cos y is never 0. Okay, cos y looks something like this. This is cos y. Let's call it cos t. And sine y looks something like this. This is sine or no, sine t. So it is 0 at one point, which is 0. Um, yeah, right. So this first expression, or this first condition is asking for sine x to be equal to 0. It needs to be, right? Since cos y is never 0. And so we need x to be equal to, a multiple of pi as kind of as above there. And then if x is a multiple of pi, well then now cos x is not 0, right? It's 1 or minus 1. And so if we want this to be 0, then we need sine y to be equal to 0, and that must mean that y is equal to 0, right? And so voila, essentially I've proved what I said, which is that sine z is 0 if and only if x is a multiple of pi and y is 0, so meaning that z is real, and it's yeah, it's a multiple of pi. So